even you can, the pay is, like I said, I told you, like 55, 50K in Irvine as a postdoc, and don't do that. So IPGA is great to learn. Combinational blocks, just the more combinational logic blocks or design modules that you guys should learn how to program it and practice with simulations and implementation to the IPGA. And it's fairly simple. And a couple of things that I didn't cover in logic, and I want to bring it up here. First, always the behavioral modeling. You'll find out you are going to do behavioral modeling for all the time in the future. This is always at X or Y. So there's no post clock or post edge clock or neg edge clock. So whatever in the parentheses, they are called the sensitivity list. And X or Y is going to be either X or Y getting changed. The signal, there's any change to X or Y, then it's going to trigger this module. It's going to update everything in the logic. Make sense? So for here, these are just like C++ or MATLAB, right? If else if. It won't update all the data, it won't do anything, or won't go through all these if statements until like X or Y getting changed, trigger. So they are called sensitive list. And another one I want to talk about is encoder. Okay. So as a combinational logic design, as other, digital blocks, let's don't think about the encoder or decoder or any digital logic circuit. Don't think about the name of it, because you can just convert it into a truth table. It's just a truth table. And then after truth table, write down all these logic equations and simplify it. Use K-map to simplify it, or just directly type it in Verilog, because computer can handle everything for you. You don't have to, do it manually. And you're done. You can design the circuit on the IPGA. Very simple. So look at this one. So the encoder requires 4 inputs and 2 output. And usually there's only one logic 1 appear for the 4 digital input. So only one will appear each time. Only one logic 1 will be in the 4-bit binary number. So the first one got D0 to be 1, and the output is 0, 0. It's just required by the encoder, okay? It's the inverse of the decoder. The decoder is you have 2 inputs, and you got 4 outputs. The 4 outputs has a 1 for each. It's like turning on the LED for each row each time. It's a decoder. The decoder can be in a different format. For example, you look from right to left. For example, the decoder has the 2 inputs and 4 outputs. Okay, 0, 0, I want to turn on D0. 0, 1, I just want to turn on D1. However, the decoder can output a different pattern of the binary numbers. It can be 1, can be 1, 0, 0, 1, doesn't matter. You can design whatever you want. But just the definition of the decoder is usually just a 0, 0, and you just got a 1 turn on. So turning on D0, you assume that's the LED over there, just turning on D0, turning on the D1 for the next one. Okay, so the encoder is just it's the inverse of decoder. The encoder just have these outputs of the decoder as the input, and then the output is a 2-bit binary number. So there will be a problem for this, since you got 5 rows, and use the 5 rows to in this truth table to find out Q1, Q0 as the output, so you can design the digital circuit. So what's the problem of this truth table for now? before we move forward? Is there any potential problem with it? So 4 inputs you need, so 4 inputs can generate how many combinations? How many possibilities, possible combinations? 16. But how many do I have here? 5. Right? I have like 11 of the different combinations are not listed. Yes, yeah, I know the customer is gonna just input one digital one each time. So what if there's an error? Like you have something, some kind of input, it's not defined in the truth table. You design a circuit out of this truth table. Okay? So what if there are some input signal combinations or patterns are not listed here? So you didn't consider it when you design the digital circuit. What's gonna happen? Yeah, if you it's gonna throw an error. It's gonna give you you only have 2 outputs, right? This is already covers 4 of the all the different patterns of the 2 outputs. So which means you have a so the example here, what I gave to you guys is, for example, D2 and D1 are both 1s. When there's an error, then you are getting 1, 1, for example. You know, it's going to start repeating the 2-bit binary output numbers because you already list all of them here. So whatever you are getting after that is going to repeating one of the 4 patterns for 2 bits, right? So which is not good. So this traditional encoder has a problem. To understand the problem, then you design, there's a improved version of it. It's called priority encoders, which can solve this problem. So how to solve this problem? That's it's another combinational logic, right? And you want to design a combinational circuit out of it. You just tell what you want to be in there in the truth table. Very simple. You start with the truth table. So what are the inputs? What are the outputs? Just tell them. Okay. So this is a bit. If you list all of the input combinations, you are getting 256. It's going to be a long truth table. Okay. You don't have to. All right. And there will be a lot of, because this only covers how many? Like 8 rows, right? So we're going to have 248 lines, which covers most of the possibilities in the truth, in the real truth table, in the full truth table. So if any bit got flipped, you get an error. Okay. So to avoid that, this is how you design it. So for the first row, you still use all the input bits and you define the 0 for all the rest of the bits. So 1 here. So for this, if I turn on D1, I need the 3 inputs, 3 outputs to be 0. Okay, this is fine. But for the second one, whenever I detect D1, I start not caring about D0 anymore. So whenever D1 happens, I just do it. Okay. Do you get that?
No. So whenever D1 gets turned on, you do whatever D1 is.
You do whatever
but if you get
you do this one, not right. Whatever. You do this one, right? But whenever this is on, you start, ignore the rest of the bits.
But if D7 and D1 got turned on, okay.
Yeah. You can see the rest. Okay. If D7 is on, I don't care about the rest of the bits. I just output this pattern. Is that going to be unique? Unique output for the desired, not desired input, but for the input I expected. Because for the encoder, whenever D7 is on, I just want to output 1 on 1 for sure. Okay, I don't care about all the rest of the bits. Whenever D6 is on, I want to output 1 1 0. Whenever D2 is on, I want to keep 0 1 0. But if D2 is on, all the bits in the front has to be 0. We are not thinking about the design of the circuit right now. We're just thinking about logic. Okay, so this is going to work, right, in theory. So how to design the circuit to make it work that way? So when you form all these logic functions, or the what's that called, min terms. So for example, for Q2, okay, for Q2, I start looking at all the ones, right? So for this row, I'm going to form a min term, which is going to be D7 bar, D6 bar, D5 bar, and D4. I'll stop there because I don't care about all the other ones. And that's it. That's everything for that min term. Okay, and so on and so forth, like all the other ones. That's how you form the logic for this truth table. For the don't cares, it can be 0, can be 1. It doesn't matter. It doesn't matter. Keep in mind when you transform or convert whatever in the truth table as a little cross, right? That means don't care. When you are converting a don't care to your main term in the logic function, you just don't care about that. For sure, you don't care about. So which means you just don't list it. Or you can put a 1 there, you can put a 0 there, it doesn't matter. As long as you think if I put a 1 there, it's going to simplify my logic function further. If it helps, you put a 1 there. If it's 0, you put a 0 there, whichever helps. Or you just ignore it. Doesn't matter. Okay. So for the logic function, you can see that for Q0, I have, for Q0 is here, right? I got the first one, the first main term is going to be D7 bar and until D2 bar, and then D1, right? See, it's here. And for the second one, second logic one is going to be D7 bar until D4 bar and D3. It's here. Okay, similar theory applies to this one. And that's how I form the logic, final logic simplified version for that Q0. So I got a Q0, but I have 3 outputs. I got 3 outputs. So eventually I have to do Q1 and Q2 as well. So this is going to be for you guys to figure that out. It can be confusing. Like, what are Q1 and Q2? Seems like I'm answering that question afterwards. It's not. It's just a question for you guys. All the following paragraphs is something else. Okay. Another chapter. All right. I'm not answering that question for you. So this is something else, which is very simple logic stuff. Simple stuff. Another thing I want to talk about is parity generators and checkers. But you have to understand that the parity generator and checker, they are not ideal error checkers. There will be still some errors. I'm going to ask you guys to answer that question, why. But let's see how this works, okay? So for example, the sensor is sending a stream of data, logic 1 zeros to my controller, sending 1 and zeros. Okay, you want to make sure that because sometimes there will be some electromagnetic interference and getting noises, probably will flip some of the bits, right? So it's going to getting errors. So before I send it, I set up the 2 systems, like so they have agreement that I'm going to send, I'm going to using even parity, the even parity number. So which means I have 100 bits to be sent, and this receiver has 100 bits to be received, right? So we already programmed on both sides, but the engineer, like they know that there will be an even number of ones in the 100 bits. How could you make sure there are even number of ones in that bit? Because digital data can be all different. Depends on the data, like temperature sensors, sensing a temperature data. It can be all different. But there are only 2 possibilities, even or odd. Only 2 possibilities, even or odd number of logic ones. So we have agreement that we are sending an even number of ones over to here to this one. So in that case, if my original data has odd number of ones, the logic circuit is going to generate another one as a parity bit and send it along with the original data. So eventually you got an even number of ones. If you have an even number of ones in there, the parity bit is going to be 0. I don't want to change it. If I add a 1 in the parity bit, which is the actual bit, it's not data. Okay. You get that? No? Just creating one extra bit. It's not data, but it's just trying to make up an even number of ones. If I have even number of ones already, there is some digital circuit can detect that. Okay, for example, I already know that I have even number of ones from the temperature sensors data, right? For example, then I'm not going to add a 1 to the parity bit because it's already an even number. Just send it over, so the checker is going to check. Do you have even number of ones? Yes. Good. Is that going to be perfect? Is that perfect checking system or not? No. What if the noise flips 2 bits? So I got a even number of ones, right? And this guy is expecting even number of ones. Oh, okay. Then the data is being sent through the transmission line, and the noise is coming, like it's flipping 2 bits. It's changing the data, but still even number of ones. So this guy is not checking anything else, but just counting like if you have even number of ones. It flips like 2 bits, 4 bits, 8 bits, 16 bits, or 124 bits. It's still checking like, that's right. That's good data. Good job. It's not perfect, right? But it's gonna, kind of will be able to, hopefully will solve some errors, some problem. For example, if there's just 1 bit getting flipped, right, and change it to an odd number of ones, but it's expecting even number of ones, then in that case, it's going to report an error. So let's don't use that data. Have to understand it's not perfect, okay? Just some way, like very simple way, we can avoid some kind of noise or flipped bits, okay? So now it's your job to implement this idea. So you have to generate that parity bit at the very beginning for the transmitter. Right? The transmitter has to generate that parity bit as an extra bit to be added to the original data. Okay, that's the original data, ABC's 3-bit data. And for example, there's a data being detected and trying to be sent. So it's 0, 0, 0. You got no ones, 0 ones. Is that even or odd number of ones? Even. 0 is an even number, right? Yeah, 0 is an even number. It is. Is it? Hopefully I'm not giving you wrong information. Yeah, let's consider 0 as an even number, right? So 0 is an even number, and then, so I don't want to add any 1 to it. Just put a 0 there, so you are still getting even number of ones, which is 0 number of ones. So if you got a ABC as 0, 0, 1, it's an odd number of ones. There's nothing wrong with the data. The data is the data, okay? But there's just odd number of ones. We need to make it up. We need to make it into an even number one. So the actual parity bit generator need to detect that and then generate the 1, so you can send a 4-bit data instead of, it's always 4 bits, right? So you have the 4 bit of data, but the parity bit is going to be 1. Okay? So on and so forth. It's a very similar theory for the rest of them. So that, whatever you need to design the digital circuit is just a truth table. You got truth table ready. Just got a circuit done. Easy, right? That's why people love logic, digital circuits. It's just simple, straightforward. And there's a huge demand on the market as well. So it doesn't mean like it's a simple thing you learn and not getting a job. It's just so many job opportunities just asking for people to program on FPGAs. Okay. You got the logic equation simplified and design the circuit out of it. And you can use this, is that structural? It's structural, right? Just XOR and G1 output, 2 inputs, and G2, right? Just 2 gates. Yeah. Don't directly use it. It has 2 different ways of modeling. Yeah. Just use one of them, right? Yeah. And so the parity generator part of this design is done. Next, for the receiver part, right? You need an even parity checker because the receiver is going to check if you have even number ones in there. And then if there's nothing happens or no error, output 0. So if you have a little LED on the IPGA, just don't show anything. If there's an error, open up just turn on the LED. So like error indicator, there's something happening. Make sense? So see that you have 4 bits, right, being received. A, B, C is the data, and P is the parity bit. Does the checker know it's an even parity system? Does the receiver know? Why the receiver knows that? You programmed it to be like work that way. Okay? So the checker knows you are doing an even parity system, checking system. So we got 4 bits, 4 inputs, and all zeros is fine, it's even, so no error. You got 3 zeros and 1 1 here. What happened? One of the four bits were flipped by the noise. Okay, so report the error. And now you got another truth table, which is significantly bigger than the generators. So you need a K-map, right? So 4 inputs is fine. You got 2 for the X, 2 for the Y, like A, B, C, P, right? It's fine. It's okay, doable. And so see, these numbers are the number of these 4 bits. Like 0 is 0000, 1 is 0001. Okay, let you guys know. Hopefully, I'm not getting confused. What are these decimal numbers? So see, this is 10 because this is 1010, right? So that's why it's labeled 10 here. But we are not using that. It's just a label, you know, by this whatever who drew it on the website. And then you put all the ones in the K-map and you can find out there's no way to simplify it. There's no adjacent cells. Why do you have to draw the K-map? You're not grouping anything. But you can still simplify it. It's not actually being simplified, really. It's just converting, recombining things, because on the K-map you couldn't group the cells, which means you couldn't simplify it. Make sense? But you can see that the logic here to here looks like this is shorter. So is that getting simplified? No. You're just changing the operators. You're changing the or and not to XOR. So what is XOR? XOR is one XOR gate has how many gates in there? Like 4 or 5, right? So we're not simplifying anything. It's just simplifying the equation, the look of the equation. And there's another parity checker and generator called odd parity checker and generator. So boring. It's no difference. It's just a different style. Okay. Just do it. And some other examples. We got 9 tasks. And for the lab today, this one, it's a 2-week lab. So take your time, right? 7 segment display and others. Let's see what are in there. 7 segment display, there's a counter. You need to know, you can set a counter because the clock on the FPGA board, just keep in mind the clock is 100 megahertz. Cannot change it. It's always, as long as you power it up, it's going to start oscillating. You can generate a slower clock by dividing that clock, but we are not, I don't think we are doing that here. So you can see that I have a parameter which is a constant. It's called count max. And what's the number here? 100 million. It's 100 million counts. And I need a 32-bit because 100 mega is not exactly 32 bits if you convert it into a battery number. But I represent this number because I just don't want to write a binary number for 100 million to be super long binary number. So I directly use a decimal number here. So that's why it's a 32-bit and it's a decimal number. Okay, so 32-bit will generate a space in the memory to hold that number. So that's why you want that number first. But it doesn't have to be followed by a binary number. It can be a decimal number. It's easier to write it down there, right? 100 million. It's difficult to do it in binary. So in that case, the clock is oscillating 100 megahertz, which means there will be 100 million positive edges. So if I got 100 million counts, I'm going to do something. Okay, so it seems like it's like a 1 hertz stuff. Anytime I count it to count max, so I'm actually giving you that answer here. If it counts to count max, which means if the clock, because every time there's a rising edge, it's a 100 megahertz clock, right? Whenever there's a rising edge, it's going to enter this block and do something, okay? If it's resetting, doing something. If it's not resetting, which is doing its business, but it has to reach that count first and then show the display. Your eye cannot resolve 100 megahertz. But it's okay if you're blinking the LED or changing the display at like 1 hertz, you can see it. I think this one is probably showing you how to. This is running LED, so the LED is running from right to left at 1 hertz. Your eye couldn't resolve it, right? It's 100 megahertz. It's gonna show what? All of them are on, right? If it's 100 megahertz running LED, all the LEDs are on for you. Your eye couldn't resolve that high frequency. So you can see that at the very beginning, I assign a 4-bit binary number to the LED. The LED is the LED on the FPGA. That's a keyword in the constraint file. So I assign a 4-bit binary number to turn on and turn off the 4 LEDs. You can see the 3 LEDs here are off, and only 1 is on. So the one on the right-hand side is on. And then I think this is reset, right? So whenever I reset it, it just turn off the 3 LEDs and just turn on the first one, LSB. If I'm not resetting the circuit, then start running. Okay, start running all the LEDs, but it has to reach the count max first, then do something. The clock is too fast. Okay, only when it reaches the count, reaches this constant, I will change that LED's bit. So first, reset the count. Does that make sense? The next time you have to count it from 0 to 100 million. So that's why every time the count reaches count max, the first thing I have to do is reset it. Okay. And the second thing here is shift the bits of the LED. You understand what's happening here? So this operation will shift the LSB to the left by 1 bit. And why? This is a curly bracket, just keep in mind. Concatenation. So LED, this is the previous LED data. Previously, LED has 4 bits, right? Like this. And this is LED 1. Yeah. This is. Yeah. And now I put this one here as an LSB. I just shift this one here. Okay? So 0 here. And I'm shifting total 0 to the left. Or I'm putting this one on the left hand side. Okay? In that way, you can shift this. Like what actually happening is you're shifting this bit to the left. Makes sense? Recombine them. The curly bracket will do that job. And then after you recombine them, change the order and assign it back to LED. So after that operation, you're getting 0010. So the second LED will be turned on. And that takes 1 second to see the second LED to be on because the comment which takes 100 million outside. Looks like it's a very simple ready LED, but the clock works very hard on it. Has to run like 100 mega times just showing you that simple running LED. But you don't appreciate it. This is joking. Does this make sense? Okay. So you can show numbers on the LED because you didn't scan them, so they show the same number. So these 4 7-segment displays, they share the same data line. You know, but how could you show different numbers on it? So in microcontrollers, you guys are going to do that with a microcontroller. You're actually scanning every single digit. So for the 7-segment display, right? Display module, you got 7 LEDs to control the LEDs to be on and off, show a different number on it. But however, for different, if you have multiple digits for the display module, you don't want to use like 7 times 4, which is 28 pins, just control a very single display. It takes too many pin resources on the microcontroller. To wire like 28 wires, just control it, give a different value there. Ridiculous. That's why they share the same data wires. They share the same data wires. So you only have 7 for data, right? For microcontroller. But if they share, every time you send the data to it, it's going to show the same number. Others show a different number. This is fundamental technology you need to learn. In microcontroller 101. You basically scan them, right? You activate it, so turn this on, and keep this off for 10 milliseconds, and you show the number, set the number here, and then you turn it off, and turn this on, and send a different number there. The microcontroller can do a reset. The IPGA can do that as well, reset. So change the number, and set it, and turn it off. Let's keep doing that. To do it very slowly, it seems like you got it. For example, you're showing 23, right? You're showing a 3 at one moment, and then after 1 second, you got a 2 here, and after one moment, you got a 0 here. After
But here it's a very similar technology that have to handle these very bottom circuit design instead of just programming in C++. This is a lot of fun, right? You know what is really happening in the circuit.
I think this one shows you somehow the way to do it. And that's a schematic of it. So I want to let you take a look at this one. A lot of you haven't taken analog yet. You can see that these are the data lines. You can see A, B, C, D, E, F, G, P. P is a point, little point here. Okay, so A, B, C, D, E, F, G are being shown here. So you know the top LED bar for the display is A, B, C, D, E, F, G, and P. Okay, so these are the digital lines turning on and off these LEDs, and they have a resistor. Is that called a pull-up resistor, or is a current limiting resistor? Current limiting resistor. Okay, you don't need to pull up anything. And you have 4 more bits here. You can see only 7 bits, right? Only 8 bits, including the point. You got 8. But you have 8 times 4 is actually 32 different LEDs. But they all share the same data line. And you got 4 selection bits to scan it. You activate one, turn it off, activate another one, you know, so on and so forth. So if you look at this PNP transistor, it's okay if you haven't taken analog yet. You have the chance to do it next semester. And you need a 0, you need a 1 to turn it on. You have to look at here first. Is this a common cathode or common anode? And what does that mean? Common anode or common cathode for the LEDs? Because all the LEDs are, if it's common anode, which means all the LEDs anodes are shorted to one point. So you must be wondering, if you short all the anodes to one point, how could you turn on and turn off specific LEDs? So what does common anode mean? I can show the circuit connection is not really clear for you guys. Let me show you how to understand this point. So all the LEDs, so see that? Represented by the red wires. These are the anodes of the LEDs. Get the plus terminal of the LED. They're being shorted to one node. The cathodes are left folded. These are the cathodes of all the LEDs. You show different displays or turn on different LEDs by having this kind of circuit in the 7-segment display module. So anode should be, you should give a higher potential to anode always, right? I got to put them 5 volts here, right? So this is like this. I got 5 volts, I have 7 LEDs. If we have higher block the other side without so this is always on. Yeah, this is always on. Right? If I turn on this one, what would I want to assign to this? 0. So I got a current flow to it. So it's on. And if you give a 5 volts here, so this is not on, right? Yeah. So you still control it. So this is called common anode configuration. Sometimes you'll see the different modules by different manufacturers that have a common cathode. Right? Just ground it here. But you want to short the anode. The lights are always on. Okay, so you can turn on and turn off. Each LED individually, get 5 volts to turn this on, get 0 volts to turn this off. So this was common anode.
anode. So how this works? How this will work?
So you understand it's common anode, which means what? So these data lines are shorted to where? To the castles, right? So how do you select it? How do you turn on here? You need a high voltage to turn it on. So you need the transistor to be on. So you need the channel to be on so you can short this high voltage to here. You can turn on individual ones. A question here, are the common anodes for each display digit, are they shorted together? It's a common anode for all the 4 digits, or is a common anode just for that digit? Why? Yes. So it's like activating it, right? Or disable it or enable it. That's how you can do the scan. Make sense? But the data line is always the same. It's the same data line being shorted to these castles for all the 4 digits. Make sense?
Yep.
Okay. Are these one here, one here, one here, one here? Are these 4 wires connected to the common anodes of each digit? So what are these lines? What are these ones connected to? Here, 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 here. They are shorted to where? To the common anode for each digit. But they are individual, they are not shorted together, you can tell. They are not. You need to individually control them, right? So if you, in IPGA, if you turn on this bit, give a 3.3 volts, which is a logic 1, and it's going to turn on or turn off this PNP, which is not covered yet, the analog, right? So you need the 0 volts. You need the 0 volts to turn on this transistor. So W4 has to be 0 volts to turn on this PNP transistor in order to short this 3.3 volts to the anode so you can activate it. Make sense? It's a switch. So for example, I have W4 to U2, right? I got 1, 1, 1, 0, and which ones are turned on? Yes. All the rest are off. Since you need a 0 to turn on the PNP transistor, like a switch, you need a 0 to turn on the switch. Okay. So when you design your circuit, your Verilog, you just need to turn on one of them each time and scan it quickly, shift that 0 quickly. And when you shift it, you need to update the data as well so you can display a different number on different digit. Make sense? Yeah. I don't think there's any difference, but I think PNP is probably better for sending logic highs, like the PMOS, but NPN is better for sending zeros. Okay. And now this is a code, part of the code, right? So at the very beginning, and you should know that these are all physical pins. So in your test bench of the IPGA, there will be a keyword in the constraint file that you can use. Like the LEDs, switches is SW, LEDs just LED, and 7-segment display I think is the SEG, which are these, right? 7 or 8 bits. You got 8 bits in SEG. So when you are before you run it, before we run the synthesis, make sure you open up the constraint file if the part of the constraint file is getting commented out, you have to uncomment. Just keep in mind. If you are using SAG, you want to uncomment SAG. If you are using LED, you have to uncomment. So what is this one? These are also 4 physical pins on IPGA, right? That's an IPGA chip. See, RTX7. That's our IPGA chip. It's just like CPU, right? So these are physical pins. So these are 4 bits over here, and they are called AN as a keyword. So you can see AN in constraint file. Make sure they are uncommented. Do I have AN here? Yes. Is this a test bench? No. So you need to design your own test bench. A bit challenging. Right? Let's see what's happening here. So this is a display module. That's whatever inside. Okay, that's a circuit design. So I have input. It must be a switch, right? The input must be a switch. So I got a switch. Which switch is on? So I want to display a number there. I want to convert the binary number of the switch combination into a decimal number display on the 7-segment display. So input here has to be a switch. And input here is X. That's the LED, probably the LED. Let's keep going. And output A to G and wire N and DP. So these are just whatever inside the chip. It's not a test bench yet. I just name it as AN, but you need to know that it doesn't matter. It doesn't have to be the keyword of the IPGA in the constraint file because these are not directly talking to the IPGA yet. These are just whatever inside the chip. But in the test bench you are writing up later, you have to use a keyword in order to make the connections to the IPGA. So AN definitely will be shorted to AN of the test bench later, okay? So DP, I just put a 1 there. If the DP is 1, I might turning it on or off. If DP is 1, it's the decimal point of the display, right? I might turning it on or off. I'm just keeping, yes, it's off. Why?
Oh wait, DP is there.
Yeah, DP is there, right? DP is one of the data lines of the display module.
Yep.
If I just give a constant like a 1 to it, am I turning that on or turning it off? Why? Mm.
But if they're the same, it won't flow.
Can I make it short? Short. The answer, make an answer short.
Oh.
So why?
Yeah.
Yeah, but it's good. It's good. Yeah, it's good. Because this data line is short to the cathode. So you need the ground to turn it on.
Yeah.
See, DP, it's just one of them, right? It's here. You put a 5 volts to the cathode, you are expecting the LED to be on? No way. Make sense? So I'm turning it off all the time because I'm not using it. That's why I just put a 1 here. So AN will be the combination of the activation. So AN will be connected to the IPGA's AN later. So you can just turn on 1 at the very beginning as the initial value. So if, for example, I'm turning on this one first, right? So what is AN should be? Like you have AN3, AN2, AN1, AN0, right? I got 4 bits. So if I want to turn on this one at the very beginning as an initial state, I should have what? Yes, 1110. 1110. So you can turn on this one at the very beginning as the initial state. And later on, just keep shifting it. Just shift, like use the way we used, in the tutorial, right? You can move AN3 to LSB and AN220 to the left, and curly bracket, so you can update it. So digit 321. Forgot what is digit. Oh, digit is 4 4 inputs of the switch. Okay. If you have, so four digits will give you somewhere up to 15. And 3 digit won't be enough. Why? For the switch, right? I'm trying to use 4 switches to input a binary number there, and I display it on a 7-segment display. However, I don't want to use 3 switches, but I want to use 4 switches to do it. Why? Yeah, binary. So the switches are just binary inputs. I'm trying to match that binary inputs and convert into a decimal number and display it on the 7-segment display. So the 7-segment display has 7 LEDs here, right? What's the largest number I can display here? 9. If I only have 3 switches, what's the largest number I can give? So if I only switch 3 switches, I won't be able to display a 9 here. Does that make sense? Can I display a 10 here? So 0 to 9, right? Can I display a A here? Yes. Can I display a B here? Okay. Or same as 8. Can I display a C here? Yes. Can I display a D here? D. Like a 0. E. F. G. Like 6. It's okay. It's not perfect, but it's going to do a lot of letters as well. If I want to display like numbers and letters and totally 17 different combinations, how many switches I should use? The 5? 4 is not enough. 4 only getting you like 16, right? So 5 will get you 32, but you don't have to use the rest of them. So that's why I use 4 switches, 0 to 3, and how to make the conversion. So I have to use it's called lookup table, right? So always at a clock, whenever the clock arrives, I'm gonna update it. Is that okay? Why do I have to wait for the clock? Why do I have to wait for you? You're so slow. I couldn't wait to see an update on the display. Is that slow? No. Yeah. It's okay. Let's just wait for it. You are not going to wait for it. The clock's waiting for you, your brain to like find out something has been changed, right? So it's okay. Whenever rising edge arrives, it's updated. It's doing that really fast. So you can assume it's just doing that in real time. But you do need something to update the circuit or the output. If there's something changes, the clock is going to update everything for you. It's running really fast, so it's okay. And whenever clock arrives, you update, you check the input of the switch. I'm pretty sure your hands cannot do 100 megahertz to change the switches, so it's okay. You just change it, and it's already updated because 100 megahertz, right? Your hands, it's probably 0.1 hertz. I don't know. Anyway, so you change it. When you change it, it's already runs for 10 megatimes already. So when you change it, it's already update whatever you have. It's real time. And if you have like 1 and 0 zeros, and keep in mind I have a hint here showing you that from MSB to LSB is from G to A. So it's GF to A. So which means this LSB is going to control. Oh, do I have a? It's going to control A, right? It's control this LED. So it's a case statement. you learn in C++. So when there's a zero, when the switch, I know it's a binary number, but Verilog can understand it. If your switch input is 0000, like a 4-bit binary number, it can understand, can convert it, not converting it, but understand that you put a 0 here, which means it's just a 0, right? Even though it's a decimal number, I just want to make it easy. So if it's a 0 for the 4-bit switch input, then let's display a 0 there. Is this a 0? Is this 0 for G to A? Only turn on G. Wait. Only turn off G. And G is in the middle. So for 0, you want to turn off that little bar here. It's going to show a 0 for you guys. Make sense? Okay. And just finish all the rest of it. Very straightforward. And this is a module, right? So this is a module, example of the module, display module. And this one is not updating that activation bit. So this one, if you just look at the input and output, wait, is it updating that? Or do I still have an N here? Oh, the N just set up an initial state for the activation. So for this chip, or this module, it only receives the switch's input and send out an output to the outside world. So we need a test bench here, which connects to the SAGs, right? Which is the 7-segment display, and also the ends. So these output from this chip or the module I just showed you guys should be connected to the SAG so you can send the data to the 7-segment display for display. And in the test bench, you need to shift AN there. So you can activate different ones. But when you shift it, you just change the data to SAG so you can display different numbers on it. So this is something you need to figure out how to update N or AN over there. But did I ask you guys to modify the code display, disable 1 and 3 of the and show the number? Oh, I didn't ask you guys to do it. So they're not showing different numbers on it. It's just static AN, static 4-bit binary number. So I think this task asks you guys to display only show the number on the one of displays, right? It can be either one. It's gonna give a static AN, like 001, 0010, doesn't matter, okay? Just turn on one of them and turn on the other ones. So we're going to do different numbers at a later time, I guess, not in here. It's okay, okay? It's easier. Any questions? Okay. I'll give a time to you guys to work on it, and we'll see you in the afternoon as well.